Okay, so the first talk of this afternoon is practical sockets in Python.
Yeah, good afternoon. My name is Floris Buynooghe, and yeah, I'll be talking about sockets. This is roughly what I'll be trying to talk about this afternoon. So basic sockets, like first in quite details. So UDP, TCP. Then we'll move on to name resolution. I found quite some gotchas in there that can snag you, and then we'll move on to handling non-blocking sockets, and then handling stream data as well, which I found to be a quite interesting topic, because yeah. And then finally, very quickly, we'll mention some libraries and other tools outside of the standard library that handle with sockets. I'd like to start with apologizing, really, because sockets are a massive topic, and it's very pretentious of me to come and tell you how you should be doing them. So I apologize for any mistakes I make. It's kind of based on my experience of writing socket code in the past couple of years, and I'll yeah, hopefully point out some bits that trip me over when writing socket code. Before we get started, the slides, the code I'll show should work on Python 2.7 and 3.2. Most of it is probably applicable to other versions of Python as well. And a really important point is sockets work with bytes. If you see a string in the slides, that's either a mistake or a Python 2.7 output, because everything is bytes. I'm not going to handle anything, converting that to text. Yeah, so from socket import star, and I'll try to be IP version agnostic. So most of it should deal with both IPv4 and IPv6. And I will not touch on any protocol design, because that's a whole. Yeah, I'll basically assume you know what protocol you want to talk. Designing a protocol is a whole new area, really. If you like Dead Trees, these are two really good books. The Python one is by Brandon Roders. It's kind of a gentle introduction, and we'll build up from the basics. I found it a really good book, actually. Covers very good detail as well as nicely building up for if you don't know much from TCP/IP to start with. Unix network programming is a C book, but it is like the reference, really. If you need to know anything that you don't know, you're probably going to find it in there. Any obscure detail will probably be mentioned in there. Yeah, the Python socket API is actually a really thin layer over the C API, so you'll find it quite directly applicable. So moving on to basic sockets. Basically, yeah, covering the common ones, TCP, IP, and UDP over IP. So the Internet Protocol is like the layer below what you usually interact with. It's basically a packet switch network, and it can deliver packets from one endpoint to another endpoint. The order of those packets might not always be the same. Sometimes packets get lost. Routers just have queues full and then they drop them. Sometimes packets get routed differently between the same two endpoints, and one of them was slower, and suddenly you got them out of order, etc. Sometimes links are not capable of carrying that big packets, and they need to chop them up, and then only one of the fragments arrives and things like that. So there's a lot of going on there. Also, IPv4 and IPv6 I think there's been lots of advertisement about IPv6 is running out, IPv4 is running out. Sorry, not quite IPv6 yet. I hope that will last for a while. But the main thing is it's an entirely different network. So the two really don't interact. Where there is compatibility is really on the OS, which has a dual stack. You can use both kind of at the same time. But on network level, they're completely separate. And this afternoon I'll mostly look at what builds on top, is basically using UDP and TCP on top of those packets. UDP and TCP, they are very the main difference is really one carries packets between two endpoints, and it's very close actually to what IP itself is. And TCP is a stream of data, a stream of bytes, essentially. And pretty much most of the things that I said about IP are classified for UDP. They may not arrive. They may arrive out of order. And there's no idea about the connection. So the kernels and the devices in between, etc., have no idea about what the two endpoints are really. There's no notion of state in there. TCP is an ordered byte of streams, and an ordered stream of bytes. And the main thing here is that it's just one long stream. There is no distinction like a packet. There's no certain length or anything. It's just an infinite length of a stream until you close it. And that has a really big impact on, I think that's probably one of the most important points. Socket objects, the methods that you use to send and receive data, will operate differently depending on, will behave differently depending on the type of socket they're working on. If you're working on a UDP, they will handle entire packets, while if you're calling the same methods on a TCP socket, you have no idea how much of the data you got. You just got some bytes, and that's it. And realizing that there's methods, the same methods will behave differently, is quite important. So I apologize if this is a little bit small. I tried increasing the font size a bit over lunch, but I couldn't do too much. This is essentially the basics of UDP. There's this surprising amount going on actually. So the very first line on the server side, I'll treat it as a classical client-server kind of thing. I create a socket with, and the arguments are the address family you want, and the address family is something like IPv4, IPv6, which are called AF INET and INET6. And then the socket type is the next argument, which is stream or datagram. This is UDP, so we pass it datagram. There is, in theory, a third argument to create sockets, which specifies the protocol you want, which would be IP proto UDP in this case. In practice, that is, if you ask for an INET or INET6 datagram, you will by default get UDP, so usually you just leave it off. We then bind the socket. Binding the socket tells the kernel that you want to listen on a certain IP address and port for incoming connections from other hosts. You may notice that if you know how to specify an IPv6 address in Python, that's not a valid IPv6 address, because an IPv6 address is a tuple of 4 elements, as you'll see down here actually. But bind is kind of strange in that it's a tuple of the endpoint you want to connect to, want to bind to, which is an IP address normally, and the port number. And Python does something handy in there. If you pass in an empty string as the endpoint you want to connect to, then it will just pick the wildcard address for in whatever syntax your host operating system actually wants to do. So if you want to bind to the wildcard address, you use an empty string. If you want to bind to a specific interface, then you want to pass in the IP address of that interface. If you bind to a specific interface, you lose the IPv4, IPv6 interchangeability. A short note on the port number. 1055 is just randomly chosen. Ports up to 1024 are reserved for the system, so on Unix systems you'll need to be root in order to be able to listen on those sockets. And there is somewhere, I forget what the actual number is, but there's somewhere a port number, and above that the kernel will use as a pool to create client sockets that connect to server sockets. So 1055 is one that, as far as I know, wasn't used. Doesn't really matter, was not used on my laptop anyway. Just an example. So the next thing, once it's bound, the kernel will actually be able to accept connections to that socket. So the next line, socket receive from, is how you receive data from a UDP socket. It's a blocking call, so that call will block until there is actually a client that connected and sends something to you. The argument you give is the 4096. Is the maximum number of bytes you want to retrieve from your socket. There is some folklore about this, that it should be ideally your page size of your RAM. It's quite, I mean, there's some, truth in that probably. Generally, it's also said that you should pick a power of 2 as well, to make the copying, etc., more quicker. The thing is, when you receive, when you pick it really small, you'll end up with just having to do lots of short calls to the kernel, and you have lots of small copy operations. If you take it too big, you're really using up lots of memory and all that. So 4096 is a reasonable number. You'll often see the double of that as well. There's one more thing with UDP itself is, if you receive because UDP is a packet, a datagram protocol, receive from will return one packet at a time. So you will always get exactly one packet. If a client sent already 2 packets and the kernel has got 2 packets in the queue, you'll only get the first packet on its own, and you'll just get that data, and you know how big that one packet was. If you pick your amount of data to receive too small, so your packet is actually larger than the data you requested, you will forever lose the rest of that packet. You cannot get it back. The kernel just throws it away, which is and then the client somehow needs to detect that or resend it, or that's up to the protocol really. But that's something to watch out for. So once it's basically blocking to get data, let's switch to the client instead. You'll notice that here for the client, I just create an IPv4 socket because I use AF INET. Because of binding to the wildcard address, the server will actually receive both IPv4 and IPv6 clients. So it's always best to use the wildcard address. You here calling send to, and again it uses the IPv4 address of the server because this is just IPv4. Send all the send methods, all the different variations, return the number of bytes they actually sent across. It's so at that point the server will be able to receive that. And if you look at the server, returns the data itself, the packet, and then the address of the client. And if you look at the address, that's an IPv4 mapped IP address in IPv6, which is a special form of addresses that they created in IPv6 space, and it basically always looks like that. So all zeros at the beginning, then 16 bits of 1, and then 32 bits, which is just a normal IPv4 address. And that's a way of making it interoperable with IPv4 on the server side, on the the last thing you'll notice is that I delete the socket object after I've closed it. Python does something weird there. When you close a socket object, it doesn't actually close the socket object. It just kind of takes your Python object that you got and makes it so that it becomes unusable. And if you call methods on it, it will just give you exceptions. But it hasn't actually closed the underlying socket. The underlying socket will only close when it loses its reference count, drops to 0, and only then will the kernel release the resources. That's a weird quirk. I'm not entirely sure why they decided to do that. The result of that is if one end closes a socket and it's not deleted yet, and the other end will still be able to send data into it, and it will just end up in the kernel buffers, and the client or the other end won't know that the data is not being read by anyone anymore, and it's only when the socket actually actually cleaned up by the operating system. Later on, I'll mention a shutdown method on a socket, which can be used to actually close, well, not close the socket really. That is actually almost impossible, but you can shut down the whole connection so that both sides will know that the other side has gone. And that's mostly basics of UDP, I think. Hopefully I've said everything on this side. Yeah, the only thing extra here is the output of netstat on Unisys. It's nice to be able to have a look. After you've called the bind method on your server socket, you will be able to see a line like this saying UDP 6 and the local address it's listening on. This is something like, that's actually the IPv6 address, that's then the call, and then that's the port number, which is slightly hard to read. But so yeah, it helps with if you're not sure what your sockets are doing to find out what's going on. There's one more thing you can do with UDP sockets, and that is connecting them. This is really only useful for when you do it from a client. If you connect to a specific endpoint, you can only receive data from that endpoint, and you can only send data to that endpoint. It allows you to use just the normal send method instead of send to. You can use receive as well instead of receive from. It's essentially and it makes it slightly easy because the kernel does the filtering for you. You don't have to check, oh, did I actually expect data from this endpoint? Because the kernel will already have done that filtering for you. So that's a benefit as well. So TCP is builds on the same kind of pattern. The extra thing here, so yeah, again, you can create an INET6 socket, and you can receive a v4 and v6 clients. So the creating sockets and binding is the same. Then the new thing is calling .listen. So when you create a server socket in TCP, it's not a normal socket that can transfer data across. It's only a socket that you can call accept on, and then it creates a new socket for you once the client has connected to it. You receive a new client socket, and that client socket can actually transfer data with send and receive as you used to. So when you create a server socket, the only thing you can really do is call accept on it. And the listen call above it, it's so accept is also a blocking call. So if a client, so if you call it, a client connects, and then you receive the client's socket that gets created for you. The listen call then is essentially saying if another client connects at the same time, then you've got two clients queued up wanting to be accepted, and the listen call specifies how many clients you're allowed to, how many clients the kernel is allowed to queue up. People usually pick used to pick quite small numbers, something like 5 or something. It depends on how many clients you want to be able to handle it at the same time. If that queue is full, then the kernel won't be able to. Then the kernel will reject the client connections, and the clients will have to go, oh, server's unavailable or something, and retry, etc. In practice, you probably need to do a little bit of benchmarking, or you can just use that constant in the socket module, SO maxcon, which is the maximum number that the kernel will allow you to use in there, which is a fairly sane default if you're actually handling your clients fairly quickly. After that, it looks very similar again. You call so you call accept, you get your client socket, and once you've got your client socket, you can send and receive data in very much the same way. And that's probably, yeah, that's essentially the special bits about TCP. If you're looking at like netstat output to see what's going on, after binding the socket, you won't be able to see the socket as listening yet. It's only when you call listen that it will start showing up as the socket is listening. Once a client is connected, you should be able to see 2 entries like this, saying because TCP is stateful, the kernel has this information about who's connected to who, and you can see the state there, so it's an established connection. And I've said this as well, haven't I? Yeah, obviously the other very important thing on TCP sockets is when you call, maybe I should go back, when you call receive or send, you don't know how much data you get here. I called receive on that and I got the entire message. That was kind of pure luck, just because I was doing it on my local host and nothing much gets in between. But it could be that when I call receive on there, because it is a stream of data without a beginning or an end, I could have just received half of it or something like that. Oh yeah, and I should say send all as well. Similarly, send all is kind of when you call just send on a TCP socket, if the kernel's buffers are full, it will. So if you send some data across, the kernel will try and send that data across. But once its network buffers are full, it will stop sending it, and it may have sent half the message by then. And then it would tell send will then return the number of bytes it sent. And if you know that you actually try to send more bytes, you then have to go and try send again with the rest of your message to put those on the byte, hoping that the kernel eventually will have space on its all its queues again. So so usually you end up having to write a little while true loop or something like that to send to make sure all your data is across. If you just call send on a TCP socket, you don't know if your data is sent across. Send all does exactly that little loop, but it's in the socket module. It's implemented in C, so it's a little bit faster. So that's yeah, the other important thing. Sorry?
Is there a receive all?
No, there isn't. Because there is no end to the stream. It's a stream of bytes. You don't have a.
4096.
No, basically no. Yeah, receive. Oh, what's happened? Receive all is just. Oh, there we are. Okay. TCP State Diagram. It's kind of, you don't really need to know that. It's good to know it exists, and you can search for it when you've got issues, and you can see trying to figure out what's going on with your socket. The one thing I will point out here is it's basically the life cycle of what a TCP socket goes through as you create it and then you connect, etc. And the different things your application can do, what it comes from the other end. The one important thing down here is this time wait state. right at the end of the conversation, because TCP tries to give you guarantees about all data is delivered in order, etc. The kernels need to do quite a lot of buffering and make and you know, reorder stuff so that you get it exactly in the right order. And right at the end, because IP, the layer they're building on, is not reliable at all. Right at the end, when they've shut down the connection, they keep the socket open for a certain time based on latency that they received on that connection, etc. before they try to do clever stuff. But they keep the socket open even after you've shut it down from the application. So if you happen to restart your application while that socket is still open, you'll get something, and you're trying to bind to that address. It will say it's already in use, and you can't use it. And that's something for server applications. That's a fairly common problem, which kind of leads us on to the next item, which is socket options. Really, from a practical point of view, there's lots of socket options, but from a practical point of view, this SO reuse address is the only one you're likely to use often. And this one tells you when the socket is in time wait state, the kernel will allow you to create a new bind to that socket again, and wait for incoming connections again. So yes, because set socket options there's if you read the man pages of like TCP, UDP, and all those things, you'll find out that each layer in the stack actually has a lot of protocol options. So that's why you have the first parameter is the level of in the stack that you want to work on, which is socket in this case. And then you set the option to whatever value it needs to be. For as a reuse address, it's 0 or 1, and that is for normal usage. That's really the only socket options you're going to encounter. Then name resolution. You probably all know the DNS system. It's fairly complex stuff, and lots of stuff goes on over the network as well. Essentially, try to not use the old v4 functions, but use the IPv6 compatible ones at the bottom. I'll talk a bit more about Getaddrinfo. GetNameInfo does the reverse, so if you reverse hostname lookup, so if you've got an IP address you want to know the hostname, not used that as often. Getaddrinfo, however, is a very complicated function, really. It's really hard to implement as well. Don't be surprised if you find it slightly buggy as well. Certainly in libraries that emulate this libs in resolver libraries, etc. libc tends to do a fairly good job of it, and it's got a bunch of parameters and stuff. The important stuff here really is the host name you pass in. You can use non there, but that's a really special case. Kind of depends on, non is normally the local host, but apart from when you pass in this special flag. But you don't really tend to do that anyway. You only tend to do that if you're creating a server and you actually ask the user what interface should I be listening on, because otherwise you just use the wildcard address and you don't need to look up any host names. Port as well. Port can be a service name, the actual port number, in which case you don't really care, or none again. None is if you don't care, and that's kind of a special case as well. That if you work with TCP and UDP, you're always going to want the port number. But if you don't care about the port number, don't put in a random port number, because you probably get bad stuff back that doesn't actually match. You use none if you don't care about it. And if you want to use a service name, basically don't use a service name, because it's the OSs all configured as differently, and they may not all be set up the same way. For example, if you try and use www in there, on some OSs it will work, or on others it won't, just because their default configuration doesn't include it for some reason. So the only thing you can do there, and that's really in the grasp of the system administrator, so the only thing you can do there is, if if you give the option to user to specify the port number, then they can decide to use a service name, and then it's up to them to make sure that that service name actually will resolve to the port number they want to use. But if you're hard coding something, just use the port number that you know you want. Don't try to put in a name. Other than that, basically the general rule is try and specify as much information as you know into the Getaddrinfo call. You get better results back that way, essentially. Flags is there's even more flags than the ones here. I'm only going to mention the canonical name one, actually. If you want to, it's a handy thing if you want to say to the user, oh, I'm connecting to this host. It's useful to know what to have. It gives you sort of a reverse lookup as well. But the important thing when you use canonical name is in the return value. You get the return value is a list of results, and the canonical name is only ever set in the first item in that list. All the other items will have an empty string for canonical name returned. So, yeah, this is an example of using it. Basically, the top example tries to specify as much as possible. But again, you know, usually this will be fine. Usually, you'll get a list of results that actually matches the endpoint you're trying to connect to. The protocol, you really always need to get at least a stream or datagram in, because those port numbers will change sometimes. Not later services anymore, because they realized that was a bad design decision to change port numbers between TCP and UDP. But it's important to at least specify the stream. But in practice, usually, if you're a client connecting, which is most of the time, as a server, you usually don't have to do an address lookup. But in practice, you basically loop over the results. People tend to just specify up to there. So saying whether you want stream or datagram socket. The one before is saying you want this is whether you want IPv4 or IPv6, 0 or AF unspec gives you both, and you basically just because so many things could be going on, and sometimes they are just buggy. You just try and loop over all the results that it gives you. Try. Do you get a connection? Then yes, good luck. Carry on using that socket. If not, just go to the next one and only fail at the end. And that's exactly what create address helper function in the socket module does as well. The only thing there is that it's only for stream sockets. It will not do that for UDP sockets. It's a slightly weird API because host port again looks like an IPv4 address tuple, but it returns both IPv4 and IPv6. And the other two parameters that are really not used that often, I find. So if you want to start from a specific source address, and timeout is another tool that standard library provides on socket objects as well. It gives you a timeout, but it's only really useful when you do simple sequential blocking calls. In practice, I find that's a fairly simplistic use case. If it's all right, it's nice for writing a quick script basically, but yeah. And then a quick note on the exceptions you get back out of socket. So the exception is always socket error, which is actually a subclass of IO error. So you could catch that as well. But if you want a nice user-readable message, you can use this error attribute, which makes that something nice. So non-blocking sockets is more interesting if you're actually doing more complicated stuff. You want to handle multiple sockets in one program, really. Essentially, the basics of it's very simple. You just call set blocking false on it, and then if you try and receive something, but there's no data sent on it, you get an exception. This time I catch it as an IO error. And if it's you need to check the error number, and if it would be blocking, you would get E would block, which comes from the error module. By the way, you have to import that separately. But if you try to do this by hand, it will quickly get messy, which is where usually tools like select come in. Select is like one of a small family of little tools that can basically multiplex, tell you when a socket is ready to do something. There's like poll and epoll and KQ on different OSs and all that. But select is also the most portable one. And if you actually end up writing a simple loop yourself, select is probably going to be performant enough, because if it's not, then you probably shouldn't be writing it yourself and use a library that does it for you. So I would say just use select, even though if it's not the fastest. The only thing here is so select. You give it a number of lists of sockets you're interested in, and you say, oh, I want to read from this list of sockets. I'm interested in writing to these sockets, and then select will return saying, oh, these sockets that you wanted to read from, this one is okay. You can read from now, and the same for the write sockets. The exceptional condition ones, the third one, is really something you don't use. There's like weird features in TCP that are like out-of-band communication, stuff like that. It's something that in practice doesn't really get used. They thought it was a neat idea when they were designing the protocols. And it's really relating to that sort of stuff. So in practice, it's not like something has gone wrong with your socket condition, as you might be misled to think. It's a sort of condition that you usually don't need for normal usage. Lastly, timeout. It's because this is a blocking system call. So you can say when you want to give up waiting for it. If you want to regularly wake up or something, you should really specify timeout. I find it in practice usually, even if I don't, if I know I want to block forever, for example, I still put it in a loop with a timeout of 60 seconds, so that if something's gone badly wrong, you have a chance of ever getting out of it. Well, one way of using this is gracefully interrupting, basically, because on your blocking calls, it's, yeah, as I said, if you blocking forever, you can never get out of it. So sometimes a way of easily waking up that I/O loop that you're writing with select is by creating this using os.pipe, which create two ends of a pipe, and you can read and write to one end or from the other, and you can use that to wake up your I/O loop. Just make sure you empty the pipe whenever you wake it up. If your loop needs to break for waking up or something, whatever, you can do that. The main thing to watch out if you use os.pipe is it actually returns file descriptor numbers, so they'll be numbers, not socket objects, which is why you need to use os.read on it and os.write rather than just calling .send or receive or read or write. So that's the basics of creating a simple I/O loop. And that kind of also brings us on to handling signals. This is something that's often overlooked, but basically your program could be receiving signals for lots of reasons. Usually you get a SIG term if you want to shut down or something, but there might be SIG hubs or user-defined signals or something. And certainly when you're writing a library, you don't know what people are going to use it for. So any system calls will get interrupted basically when there is a signal, and they'll stop, and you'll have to restart them. This is not actually a bad thing, really, but despite the fact that it's actually quite annoying. because if you're in a blocking call, you want to, and someone sends you sig term, and you want to do some shutdown logic on sig term, if it was a blocking call, you would never get out of it unless you do get that. If you're writing in an I/O loop, you probably have a mechanism of waking up your I/O loops separately, and which you can do from a signal handler or something like that. And in that case, you need a little while true loop to just keep receiving if you get interrupted. Yeah, in blocking code, be careful that you don't get your signal if you want to get out of the application, then just go and restart it again, and then you're blocked again. And as a library, you need to be slightly aware of that as well. If you're writing just a simple application, you can use this in the signal module, sig interrupt. You can say, oh, I don't actually want to be interrupted. So Python will just, for you, restart the system calls. But that's only if you control the whole application, really. And then handling stream data is an interesting topic. I'm running out of time, so I'll have to go through that fairly quickly. Basically, because on TCP it's just a stream of bytes. You need to somehow. Generally, you need to have a buffer and collect those bytes until you got enough of them, and try and pass a packet or a frame, as I'll call them now. This is just an example protocol header. Doesn't really matter. The nice thing about this protocol is you've got a fixed header length, so you know how much data you need before you can read your header, and that usually the headers will say how much other data you need to wait for. So basically, on your protocol layer, you'll want to send and receive frames, and you need to do buffering to be able to get the whole frame at a time. There's multiple ways of doing this. The I/O module, which is I think new in 2.6, gives you I/O.bytes. In 2.6, I think it's still quite slow. I think they rewrote it in C for 2.7 and 3.x. So it's basically string I/O. I'm sure you all are familiar with string I/O, but it will ensure you get bytes, and it's compatible with Python 3. So that's why I prefer to use it, and it makes it actually working with bytes. So yeah, you can keep writing to that. The other easier kind of method usually is using a list of strings, and you just put strings together. The reason sometimes you might want to avoid that is if you're receiving data, you might get it in small bits and things like that, and you end up with quite fragmented memory. So that's usually, if you do it by hand, usually I tend to go for receiving data with I/O, byte I/Os, and sending data with actually strings, a list of strings, because sending, usually your protocol layer will say here's a whole packet, and that's a fairly decent unit to try and send at one go. If you got entirely fixed data, then you can use byte array, and you can save some more copies. With byte array, you can also, if you know how much exactly you expect, you can use copy into, receive into is another socket method, and you can save copy operations of long strings. This is an example of receiving data with byte I/O. I'm going to skip straight past it because there's not enough time for it. And then similarly for sending data. The next thing, though, is the next thing. Makefile basically is a method on your socket that tries to do buffering of data for you. And generally, if you can use it, try and use it, because it will make your life much easier. I'll go to the example actually, which is on the next slide. Basically here it's the easiest way of using this is if you've got a simple protocol that uses a socket just for one request response kind of thing, and so the client can send a request, and then it shuts down its write end of the socket. When it shuts down the right end of its socket, you've only got half a pipe left essentially. The server will notice that and see that as an end of file. When you're reading from, so the server, should be all familiar. When you accept and on the client socket you call makefile, and you read data from that. If this client had only sent seven bytes across and hadn't shut down its end of the pipe, read on a file on the file-like object that you get back will block forever until it gets end of file or the required number of bytes. So that's why it's usually easiest if you can shut down one end of the pipe. Similarly, then you can write until the end, and then then the server, if the client had been using makefile as well, the server would do shut down its sense of the socket would shut down as well, and that way the client would be able to get end of file as well. So that's the easiest way of doing it. If makefile, you can use it if you don't want to, if you want to keep reusing your own socket for multiple requests and responses or whatever it is you're doing. But you really need to know how much data you're going to get, because it's the read till end of file is kind of annoying, and if you don't know this, then like trying to read the headers of HTTP, for example, or something like that, you're going to have to do it in 1 byte at a time or something, and that becomes really inefficient as well, because even though there is buffering behind the scenes, you're doing lots of loops and copy operations on very small amounts of data. So that only really works if you got fixed amounts of data in your protocol. You can use non-blocking with this as well. It just means that you read in a flush operation is like making sure that all the data you done in write is actually sent. But they can raise a would block if you get that wrong. Cool. So basically, multiplexing I/O, like handling multiple sockets, multiple clients in the server side is quite difficult. And writing an I/O loop with select, it's fine for simple cases. But if you're doing something serious, you should probably try and see if someone else can already do this. Because there are libraries that do I/O loops already. I'll mention two kind of approaches. Greenlet is kind of a lightweight. It's based off stackless Python, but it's an extension module for CPython, and it allows you to basically juggle stacks. Well, it's a bad explanation. It allows you to take multiple user level threads essentially in one kernel level thread, and that will become obvious when we get to the example where that's useful, because when you're doing I/O, you don't actually want necessarily to process multiple things at the same time. You've got a global interpreter lock anyway, so that's a neat solution of quickly switching. There's like three projects that are based on Greenlet, Eventlet and Gevent, and then Concurrence is kind of, I don't know how alive or how much use that is, but I've never used it myself, but it looks actually quite interesting. But basically, Eventlet and Gevent are quite similar. They kind of run a hub with this I/O loop in the background. They have different approaches to how they actually implement it. And basically they change the socket implementation. So instead of using the native socket, they will go and automatically switch to a hub. So in the top example, which is just a client connection, when you do connect, that's normally a blocking call for a client in TCP. And it will, when you do that connect, instead of blocking in Eventlet, you will switch. It will switch to the hub, and the hub will use this main loop, which does something select-like, and only switch back. So if you look at the server example, it illustrates this nicely. So you're accepting client, which is a blocking call. So that this will switch to the hub, and the hub will then switch back to you when you got a client, and then you spawn a handler in a way. And after you spawn the handler, you just go straight back into accept, and you're trying to accept the next client, which will switch back to the hub. And then the hub will say, oh, but I got another tasklet or green thread, whatever that you want to call it, that's got something to do. And then it will switch to that one, and that one will then be able to receive its data, etc. Again, these calls block, so if there's not enough data ready, it will switch back to the hub and be ready to switch to another tasks. So that's how Eventlet and gEvent is very similar, as far as I'm aware. Kind of handles that for you. Twisted is kind of, I think, obligatory to mention in when you're talking about sockets. It's a framework approch. So you kind of have to design your application around it. It's not a library that you're just going to use. The no one likes frameworks and no one likes callbacks thing is my personal opinion. Yeah, it's callbacks based. And I know there's this tool called inline callback or something that kind of makes it easier. But I find it really awkward to use, really. On the other hand, it is very, very complete. They have implemented lots of protocols for you. So if you're happy working in the twisted framework kind of thing, it's very good. It's very mature, and it handles a lot of edge cases that you probably spend a lot of time finding yourself. So that's the upside of twisted. Yeah, but yeah. So yeah, in general, I find. Don't be afraid to use sockets, but be aware of actually handling them correctly. And yeah, if you need lots of clients or something, don't try and do it yourself, because someone else probably figured out already how to do that. I'm a bit over time. I apologize.
Cool. Yeah. So if there is, we have time for 2 questions. If there is any.
On the second or so slide, when you pass an empty string to bind, I believe it was, and you said, thanks to some magic, that will bind both an INET and an INET 6 protocol. That one.
That one. If you look at nets and output, it will show us listening on. This is UDP, so you'll see on the, I think on the next slide, it will show up as a UDP 6 socket, okay. But that UDP 6 socket, or if it was TCP 6 socket, will be able to receive connections from both.
Is that Python magic or operating system magic?
That's operating system magic.
So OS dependent?
No, they all, well, in my experience, they okay. all seem to behave that way. That's the way that the standards are, I think, are supposed to be.
Fair enough.
Specifying.
Second question, if I may. When you call makefile from a socket,
yep.
I believe Windows has the restriction where you can only use select on sockets. So presumably after you've used makefile, you can no longer use select. They're not special file that still work with select.
Yeah, your file object is... you have to do select on the socket object behind it, I think, and then okay. you can use the file, and then you can use the file object.
Oh, I see. Okay.
Because you still have your socket object, you don't throw that away, so you can do select on that.
Fair enough. Okay, thank you.
There's time for one last question. Okay, so thank you. Ravioli è finito.